The director of research and development is testing a new drug. She wants to know if there is evidence at the 0.05 alpha level.
Okay, alpha equals 0.05. Go ahead.
That the drug stays in the system for more than 302 minutes.
So we have a null hypothesis that mu is less than or equal to 302, and an alternative hypothesis that mu is greater than 302. Okay, go ahead.
For a sample of 31 patients,
N equals 31.
the mean time
X
the drug
bar,
stayed in the system was 304 minutes.
304, okay.
Assume the population standard deviation
Sigma equals
is known to be 23.
23. So one of the first things we want to know is what is sigma over the square root of n? Because we're going to need that later. So let's calculate that. It's 23 over the square root of 31. And what does that come to?
4.13.
4.13. Okay, so we have that. Next, we want to look at raw-score space. And we know we have a bell-shaped that's centered around 302. It goes from minus infinity to plus infinity. And so this is raw-score space. And then we have a alpha here. Alpha is equal to 0.05. Then we want to look at standardized space because we can't go from raw-score space directly to probabilities. We have to go via standardized space. So standardized space is always centered around 0. We go from minus infinity to plus infinity. And we also have some cutoff, some critical value that gives us an alpha equals 0.05 in the tail. Okay. So now what do we have next? Well, we've got to find out where this x bar value falls. We'll presume this x bar falls here. So x bar is equal to 304. So if x bar is at 304, then we have to find out how much probability there is to the right of x bar under this bell-shaped curve. So we'd have a similar cutoff value here. Somewhere to the right is the p-value. The p-value is this probability. So the p-value is the red probability, the p-value. And so we want to be comparing the p-value, this red probability, with the alpha level of 0.05. So we want to find out what this p-value is. So to do that, we need to take this 304 in raw-score space and standardize it to get it into standardized space so we can then look for the probability. So we want to take x bar minus mu 0 over sigma over the square root of n. And so we take x bar, which is 304, and we subtract our 302, and then we have our 23 over the square root of 31. We've already calculated that. In the top here, it's 2 divided by 4.13, and when we do that division, what do we get?
0.4813.
0.4813. And of course, we only get the two decimal places in our z table. So when we go to the z table, we look for the 0.4, and in the row is 0.4, and then we look for the column that picks up the additional 0.08. So we get our 0.48. So then what probability do we find?
0.3156.
0.3156. So what happened here is we found that we had 0.4813. This was the z-value. A z-value, the z, you can call it z sub p for the p-value. So over here, we could call this the z sub p, because it's the one associated with the p-value. And so we found that this p-value is 0.3156. So we know that these probabilities are preserved. So that means the p-value is up here, 0.3156, and we can see that that's considerably larger than the 0.05 because we're comparing with the 0.0500 if you want, and we can see that the p-value is larger than the alpha level. Therefore, we fail to reject the null hypothesis, and we say that this new drug does not give us a value greater than 302. It's the conservative position that the new drug isn't any better than the old drugs. That's it.